So as typical, there are many co-workers on this presentation. I just wrote many colleagues. You find most of them on the appropriate journal articles later on. I find more essential than just such a presentation. Okay, we are concentrating on the Norway-Greenland Sea. Here you see Greenland, Svalbard, Norway, Iceland, and in between the Jan Mayen fracture zone and the Barents Shelf, that is the Norway-Greenland Sea. And I'm going to focus on the Greenland side. North Atlantic is particularly well explored generally, but the Greenland side, of course, due to the ice, is less explored than the Norway margin here on this side. So this is bathymetry, or this is magnetics, the study area indicated. And from the magnetic lineations, you can already see that there is an issue with the continent-ocean transition. You might get the impression that the oceanic spreading anomalies are continuing far onto the shelf area, means in that area here. So it is not really clear where the transition from continental to oceanic crust takes place. The second well-known fact here is that there was a lot of breakup-related magmatism in those pink colors here, or violet colors, again, Mayen microcontinent, and also the Scandinavian margin is highly magmatic during the rift phase. Wrong direction. Here we are. If we are talking about magmatism, volcanism during rifting, we come pretty often to those seaward dipping reflectors. This is an image from an outcrop in West Greenland, here from central West Greenland, the Svartenuk area, where we have these nicely seaward dipping volcanic flow units, dipping at an angle of about 20 degrees, dissected by many faults and also by numerous dikes that cut across these flow units. In the really offshore area, we typically image those flow units as SDRs. Their name was simply to describe these seaward dipping reflections you see on seismograms from the continent-ocean transition. And that is an example from the early days from the conjugate to our study area, the Werin margin, an area that actually was drilled. So we are confident that these are magmatic units, lower flow units, and the inner SDR wedges here separated by a strong unconformity. A modern example might be the East African rift system. Here an image from the Afar area in Ethiopia, where you have a rift basin and the volcanics filling up that basin, flowing out to both sides. And later on, when we expect breakup in the center, those flows are expected to dip in a seaward direction, either due to subsidence, simply gravity-driven subsidence, or enhanced by faulting. Those are expected to result in an image like this here. No, it's going in the wrong direction. So here we are. This is the grid of seismic lines we acquired in 2017, close to the ice edge. So the ice was up here, and we were able to acquire conventional 2D multi-channel seismic plus gravity and magnetic data along these lines. This would be the 1,000-meter isobart here, and here you see that the magnetic anomalies intersect with that anomaly and might extend onto the shelf. So we cover exactly the continent-ocean transition in here. Few volcanics are outcropping onshore, mostly of early Eocene age here. So the first question now is, what is the origin of the magnetic anomalies at the slope and in the shelf area? Though this would be the shelf, the slope, and that would be the deep oceanic basin. And imaged down here are two wedges of seaward dipping reflectors. We assigned to them magnetization and the gravity from values we did know from that drill here at the conjugate margin. And of course, we model the magnetic signal, the blue line here, That would be magnetics, in red, that is gravity. That is certainly not a unique solution, but two things become clear here. First, this is not what we term oceanic crust. That's different. This is really an area covered by SDRs. And second, the magnetic signal is coming from that depth, from the shape and the structure of these anomalies. You need to explain those magnetic anomalies by bodies at the appropriate depth of the SDRs. One might argue that the magnetization, we had here a negative and a positive on top, models to fit the lineation of this may be varying. This is a non-unique solution, but it is clear that the magnetic signal is coming from that depth and then therefore from the SDRs. So once we are confident that the SDRs are causing the magnetics, we can derive a relative timing from the position of the SDRs with respect to the magnetic anomalies. That's a seismic line from the northernmost part of our study area. From here, where the first clear seafloor or spreading anomaly C24b is very well expressed in the oceanic domain. And the SDRs here, two wedges with a very nice escarpment similar to the Bering margin. Those SDRs are clearly positioned landward of the magnetic anomalies. So that means these were in place before that anomaly did develop, and this means we have a timing for these. That's probably C25 or possibly older, but the upper limit is in the late Paleocene. These are pre-Eocene SDRs here. So the next line to the south, that was a line we have seen before. Next one here with the two wedges. One is located in the vicinity of the extension of C24, and the other one is associated with C23. So we have a decreasing age of the SDRs over the 100 kilometers in that area. This Seaward, so that is a zoom of this box here. The Seaward SDRs are much more developed than the landward ones. These are pretty similar to the lower flow units on the conjugate Bering margin, but this Seaward portion is shows the image of a typical inner SDR wedge. So a relative timing issue can also be derived from such kind of composite sections here, the upper part. This is the lower section. And if you are following the top of the SDRs, here again, the nice escarpment, the top of the SDRs ends up in the sediments here, and the top of this SDR wedge comes to the base of these SDRs here. The same here, you can follow the top, and you will end up at the base resulting in individual wedges being emplaced at certain time stages during the rifting. Even further south, we are landward of the prolongation of C24, and the SDR size generally decreases to the south and to the north. There's another magmatic signal in the data, not in the form of SDRs, but massive magmatic edifices in the seismic data. And these were emplaced later from the relationship with the acoustic basement that dips down here. And this should have the age of the breakup of the Greenland Sea. So there are sediments emplaced in between before these volcanics came in. And with our seismic stratigraphy, we have tentatively identified the top Paleocene reflector that coincides more or less with this phase of magmatism, and that was Oligocene or earliest in the latest Eocene. So there was a second pulse of magmatism in this area. If we summarize, we have these individual SDR wedges, number one being emplaced first, and then came in number two, number three, seaward of number two, and maybe at the same time this seaward portion came in, and then the fourth phase in here before during a later stage, a second breakup stage, these volcanic edifices, including possibly structures on the seafloor far out, were emplaced. So what we found is first the SDRs are the origin for the magnetic signal at the slope. And that means that there's likely continental crust beneath the inner SDRs, as has been proven by drilling on the conjugate margin. That means the oceanic crust terminates somewhere out here. We identify a 2 to 4 million years time frame for the emplacement of these SDRs. And that took place in several segments of the margin. So the rift obviously was segmented and the volcanism concentrated on the individual segments. And generally, those volcanics were emplaced from north to south here, similar to the pinch out of the seafloor spreading anomalies. So seafloor spreading also went from north to south here.
10 minutes.
Thanks. Overall, if we combine all these SDRs, we have an image like this, and we propose a central injection center from the decreasing volumes of the SDRs to the north and south here. We already saw the pinch out of the magnetic anomalies that indicates a north to south opening of that portion of the Northeast Atlantic. And there was a prominent late Paleogene, probably Oligocene magmatic finding from that margin to the conjugate whirring margin. The image of the inner SDRs here in red is pretty similar. We have decreasing volumes to the north and south, and likely one or more injection centers in the center of those SDRs. And that is obviously a more widespread finding from the West Greenland area. We saw the example before. We know that all these SDRs in the Svartenhoek area and also in that area here, they came from a single injection center, a nice little island, the Upengek Island, and via dikes, those magmas were transported and then formed later on these SDRs in the two areas. There might have been another smaller injection center here originating the Disco Island SDRs, and also from East Greenland. There are reports on Dutch injection centers with radial dike swarms coming from those local areas. And from my point of view, it could well be that this idea by Laurent Joffre of local points of weakness in the lithosphere or uplifts of the lithosphere are the origin for the individual SDR and volcanics that we find along the margin. They may be related to the rifting process itself, or maybe resulting from inherited structures. So to conclude, we have indication that the Greenland Sea initiated from limited segments. So the rift that resulted in that ocean was segmented into compartments a couple of 100 kilometers long. And in the early stage, there was not a clear initial propagation direction, but more kind of punctual seafloor spreading as we observe it in the Red Sea right now. We speculate that melting was localized, and the configuration of the lithosphere might have guided those melts to the points where we identify those today. The breakup itself was oblique, and as we can identify from the pinch of the seafloor spreading anomalies at the western margin, while the eastern margin we have more or less parallel seafloor spreading anomalies throughout. So that's from my side, typical thanks, and thanks for your questions.
Thank you very much, Dieter. Very interesting talk. If you like, you can type your questions in the chat And while you type, I would have one question to kick this off. How representative would you say is this magmatic margin that you just discussed for other margins of the world, for other magmatic margins? Would that be a prime example or rather something that sticks out?
That's a question, yeah. So, well, I have seen a number, but not of course not all volcanic margins so far. With respect to the volume of magmatism, the southern Northeast Atlantic shows much more volume, and although the South Atlantic is much higher in magmatism during breakup than this northernmost portion I have studied here. In general, I would say it is representative. We have all the features that should be present at the magmatic rifted margin. But in detail, we identify, the better the data become, our group identifies more and more specific issues at either margin. So I would say it's difficult to find the representative margin.
Okay, thanks. Gianretto, you have a question?
Yeah, you said that the formation of magma was localized. So my question is the transport of the magma localized and it's actually fed from a wider area, or do you think that it's really a localized area that is melting and that leads to these overlying SDRs?
Well, I mean, if you compare the size of the margin with this onshore outcrops here, what we have studied is exactly the same size of the margin. And here we are pretty confident that there are just two of such centers. So I would speculate that this is caused by 1, 2, maybe three centers that are the origin of all these SDRs and flow units at the margin. We cannot prove it because we do not resolve the dikes and the seismic data, and we would need to show the dike trend to really be sure they point to a common location that can't be shown. So we just can derive some ideas from analogs, and for me the West Greenland area could be such an analog.
Yeah, my question was much more about what is the width of the melting mantle underneath, and is there a sort of a channeling of the magma in the mantle, and is it focused while it goes through the upper lithosphere?
I have no idea how to derive from any extent of melting mantle 54 million years ago. So in that case, I would try to look at the East African Rift, the Red Sea, for example, and see if there are estimates for the mantle that is involved in the magmatism there. But here, if it is so long ago, I would say this is just speculation. Or for me, I have no idea how to answer your question, sorry.
And let's move on to the next question. Suzanne is happy to have Toines Hein ask a question. Could you ask it yourself, please?
Yeah, so in the Afar region of East Africa, there are rifts that have magnetic stripes associated with them. So the implication of what you were saying is that where the magnetic stripes are that you've identified to the southeast of your SDRs, that it automatically represents oceanic crust. But that's not the case in the Afar. So what defines the oceanic crusts in your study other than the magnetic stripes?
Well, I would say we have a lot of evidence that you cannot conclude from the presence of magnetic stripes on the presence of oceanic crust. That is not only true for the SDRs, also exhumed mantle from time to time may show that kind of pseudo seafloor spreading if there's magmatism going on in between. I would say this is pretty robust by today, that this definite relationship isn't there. And then we need to define oceanic crust. I mean, the SDRs are mainly mafic. Only the inner portion are likely placed over continental crust that we do know from many ODP wells. So yeah, it is, the difference is not mainly the composition, but the form of emplacement and the excess volcanism that is present during the formation of volcanic rifted margins that make the huge difference to what we term usual oceanic crust.
Normally I would break off the questions now, but since we have a bit more time because one speaker dropped out, I think it would be good to have Manuel's question next, and then maybe keep the other questions either for the chat or for the general discussion in the end.
Yes, thank you, Dieter, for this very nice presentation. I was wondering about those sediments below the first SDRs. Do you consider that they are sort of end of scene rift period, or are they already post rift? It seems that they follow a sort of sag of the margin. They're deep towards the sea also, don't they?
You're referring to that 1000 portion here where we saw that example with sediments in between?
Yes, I think it's this one, yes.
Yeah, then it was kind of post-rift, because breakup of this northern portion of the Norway Greenland Sea took up 20 million years before breakup of this portion south of the Jan Mayen fracture zone. So we have we have a time difference in breakup here. The northern portion broke in the early Eocene, and the breakup here is not really well known, but should be in the late Oligocene to Miocene. So, right. And that would be ample sufficient to allow the emplacement of all these settlements in between.
Okay,